So let me go through just the web page real quick. So I sent an email on Monday after class, just sending you the links, for where the information is. So again, this is my homepage, and there's a link for the course, and again, all the PDF notes that I present in class. Oops, not that. Wait, what am I doing? The notes for what I present in class, they're all online there. All right, so this is what we did last time, and after today, I'll update this again. And all of the announcements and discussions and things we have outside of the main lecture will appear on these links here under whatever date it was. There's January 11th. That was Monday. This is the first homework assignment. That's up there as well. Okay, and that's due on Wednesday the 27th, 2 weeks from today. Solutions to homework, solutions to exams, they'll be here as well. The updated class policies, and I got the date and time correct now for the final exam. All right, so all of the content, PDF content for the course is here on my personal webpage. And then on the YouTube channel, I'm recording the lectures or the sessions that we're having under, I'll put them under the date on which they're given. So Math 2800, January 11th. There is a playlist for it, Math 2800, Spring 2021. So 80s and A. 65. And there's the lecture and discussion from last time. Any other ideas? Any words you've seen? So I apologize for the hodgepodge of web pages, but I'm not going to be posting any content aside from your grades on Pilot. So if anybody cares to know the reason for that, I can fill you in some other time. Any questions about anything before we get back to the lecture? Anybody, any questions? Again, please, speak freely. It's a small class. We've only got 12 students, 13 students. So there's no need to, always type questions and raise your hand formally. Just speak freely, please. Anything, any questions about?
Yes, I had a question about implication.
Sure, yeah. Yeah, we're gonna go.
So I was looking over
before we get back to that. Just anyone have any questions about the mechanics of the class or anything of that sort? Okay, all right. I'm sorry. Go ahead.
Okay. I was just kind of having trouble with the English to propositional logic statements.
Yeah, we're going to go over a bunch of examples of that. We just didn't get to it really. We didn't get to much.
Oh, okay.
Yeah, we'll go over a bunch of examples of that.
Okay, thank you.
Yeah. So, all right. So right back to the lecture then. So just a quick recap from last time. A proposition, there it is. A proposition, right? It's a statement, a sentence, or a statement is a sentence in the English language that's, well, for us in the English language, that has a definite truth value, either true or false. So some examples here. And then you can take statements or propositions and connect them with connectors to make larger propositions. So the first connector was conjunction. That roughly corresponds to and in the English language. But there's other ways of stating conjunction in English. A and B, A furthermore B, A moreover B, A however B, A but B. Or you can just put two sentences together, and that's sort of an implied and as well. So the truth value for A conjunction B is given in this column of this table, given the four possible truth values for A and B individually. And then there was disjunction, roughly corresponding to or in the English language, and there's a truth value there. And then implication, and that's where we left off. So implication is important, and it's probably the most confusing of the connectors. Given propositions A and B, A implies B has the following truth value. So it's true in these rows and false in this row. So only false in one instance. So in the statement A implies B, A is called the hypothesis and B is called the conclusion. Okay, so a few things to remember. Okay, the only time the implication is false is when the hypothesis is true and the conclusion is false. And that's it. That's the only time an implication is false. In all other instances, it's true. In particular, when the hypothesis is false, the implication is true. When the hypothesis is false, the implication is true. When A is true, the implication is true. B is
The conclusion is
irrelevant. Okay, that's because the convention in propositional logic is just that. That's a convention. If I was to say to you again the example from last time, if you're you're a parent and you say to your small child and your parent says to you, if you eat your vegetables, then we'll have ice cream. If you eat your vegetables, then we'll have ice cream. So if you eat your vegetables and then you get ice cream, that means I told you the truth. If you eat your vegetables and you don't get ice cream, it means I lied to you. If you didn't eat your vegetables, I said nothing about that. Okay, so we say the implication is true, although it's not true in a satisfying sense, right? It's said to be vacuously true, but you have to have a convention, and again, there's reasons for that convention that you'll see. All right, in English, implication has got lots of ways of saying it. So standard ones are A implies B. And then if A, then B. These are the two clearest ways of stating implication. A implies B, or if A, then B. Other ways of saying it are less clear, although they're used. B follows from A, B when A, B is necessary for A is sufficient for B if A. What do these all have in common? These all describe a relation in which A is true, a relation in which instances where A is true are contained in the instances for which B is true. So it describes a containment relationship, that the instances of A are contained within the instances of B. So having A implies B. If you have A, then you're going to get a B. Right? All apples are, let's be, like all apples grow on trees or something like that. All apples grow on trees. Not that everything that grows on trees are apples, but all apples grow on trees. Okay, if you got an apple, you got something that grows on a tree. All squares are rectangles. Right? Not that all rectangles are squares, but squares are rectangles. Right? All students in my class are students at Wright State. Right? All students in this class are students at Wright State. So B follows from A. if B follows from A, which containment is it? Is that B is contained in A? Right? I mean, if you're confused about, which is which, it's not this one. Write them both down. So, let me see. Let me do this a little bit better graphic here, infographic. All right, so this is the relationship. So let's make it thicker. Oh, I need thinner. And so it looks like this. A contained in B. All right, not B contained in A. How do you tell the difference? So here is an instance where A is true, B is false. Here is an instance of A is true, B is false. Something outside the instances where B is true, but inside the instances where A is true. And that goes against what the statement says, right? Here is an instance where A is true and B is false. Does that contradict that B follows from A? If it's possible that A is true and B is false, does that contradict B follows from A? B follows from A, yet I have an instance where A is true and B is false. Is that a contradiction? Do they contradict each other?
Yes.
Yeah. Yeah. B when A. You get B when you get A. You get something on a tree when you have an apple. So yeah, here's an instance of an apple that doesn't grow on a tree. Yeah, it's a contradiction. B is necessary for A. Right? It's necessary to go to a tree to get an apple.
So it's only false if B is true and A is false. Is that what you're saying? Or is it only false if A is true and B is false?
Exactly.
Okay.
Exactly. Yes. It's another way of looking at that truth table. So I mean, all these things are implication, which all describe a containment relationship. So if you're confused about which is which, look at the two containments. Is it A that's contained in B or B that's contained in A? Right? It's this one. So, and to use the Facebook parlance of the day, everybody says this rather than not this. This, not this. Right? It's this containment. B is not. A is sufficient for B. A is sufficient for B. If you're gonna get an apple, if you're gonna pick an apple, you got to go to a tree. Right? So here you have this B is necessary for A. So B is the big thing. I think I switched here. A is sufficient for B. A is sufficient for B. Sufficient means when you have A, you're going to get B. It's sufficient to give you B. Not that it's everything that B is. B if A. You get B if you have A. And the one I really can't stand is A only if B. So just to be really confusing, B if A. So you get B if you get A. You get A only if you get B. I mean, it's about as twisted as it gets. Okay, but they're all implication and they're all said. Nowadays, people try to be more precise about, you know, about what they're actually trying to say. So, folks really try to stick to A implies B or if A, then B. If you go back to, say, like 19th century writing, so the end of the 1800s, I mean, it was fashionable to be like confusing, and all these different things were used, like all the time, rather than A implies B or if A, then B. Like they were trying to confuse you. It was a mark of being educated or something. I don't know. All right, so we'll get to examples of translations in a moment, but that's the quick introduction. So more connectors. One more connector. Or no, two more connectors. Excuse me. So that was third. Fourth, logical equivalence
or double implication.
or double implication. Logical equivalence, double implication, and why that's double implication called that. We'll talk about it later. Double implication. It's a double arrow like this. So given propositions A and B, the proposition A if and only if B is the following. So in English, A, and it's usually said if and only if B. A if and only if B. Or, folks might just say A is logically equivalent to B. And essentially, it's sort of logical equality. So it's equality of truth values. A if and only if B is true when A and B have the same truth value. Both true, A if and only if B is true. Both false, A if and only if B is true. One is true and the other is false, then A if and only if B is false. It's the opposite of the exclusive or, right? When we defined disjunction, it was the inclusive or, right? Either A or B or both. But if you want to say if you want to say A or B but not both, it's the opposite of this. It's false, true, true, false. So this is the opposite of the exclusive or the negation. And that's the last factor that we're really going to talk about. Negation. And we're going to use the apostrophe notation for it rather than the sort of squiggle in the front. It's more, it's easier this way, I think. Given proposition A, so in English, is read as A not, or not A, depending on where you like to place the not. A not or not A. And it's not really a connector per se. I mean, it just has one argument. So if you have A, and A is either true or false, then A not has the opposite truth value, which is like this. Okay, so if you negated A if and only if B, then you get the exclusive or. All right. Operator precedence. Okay, so as with arithmetic of real numbers, right? Only two numbers are connected at a time. Well, let me say it differently, I'm sorry. So in the arithmetic of real numbers, we use operator precedence to reduce the number of parentheses used. Right? In particular, multiplication has precedence over addition. Right? So when we write like 3 times 5 plus 7, right, this is equal to 15 plus 7 equals 22. But we don't write 3 times 5 plus 7 because it is understood that multiplication is evaluated first. Okay, if we want to write 3 times 5 plus 7, right, which is equal to 36, then the parentheses are necessary. Right? So, but we have that precedence to cut down on the number of parentheses that are used. So with propositional logic, operator precedence is as follows. One, negation comes first. Two, conjunction and disjunction comes second, but neither one comes before the other. Three, implication comes third. Fourth, double implication, so is last. Okay, so for example, when I write this, A and B arrow C, we mean A and B comes first, and then you do the implication with C. Okay? If we want to write is different, well, sorry, which is not logically equivalent to, and we'll see that. Oops. A and B implies C, where the parentheses are necessary. Okay, so when we write this, we mean that. But we don't put the parentheses there because it's less cluttered, right? Just like with ordinary arithmetic. But if you want to write this, I mean, which is fine, if that's what you mean and that's what you want to write, then you can write it. But you definitely need the parentheses in order to say that we want to do this implication first. Okay, so another thing which really needs to be said neither conjunction nor disjunction has precedence over the other. What does neither nor mean, by the way? Neither nor. Neither this nor that. Just since I wrote it down, what does that mean in a logical sense? Neither this nor that.
Isn't that like negated and? No.
What do you mean specifically?
It's just saying that both of those aren't, I think.
Right. That's what it is. It's conjunction.
Oh, yeah.
Nor that, right? Neither will you leave your house, nor will you gather with your friends. Sorry.
So it means both are
Neither
false.
will you leave your house, nor will you gather with your friends. It means you're not going to leave your house, and you're not going to gather with your friends, right? So it's conjunction, not this and not that. And actually, it's interesting because it's a English language construction for something called De Morgan's law, which we'll talk about in a little while. I'm sorry, you had something you wanted to say? Somebody was speaking?
No, I'm okay. I get it now.
Yeah.
I was just.
Yeah. Okay. All right. So neither conjunction nor disjunction has precedence over the other. Therefore, writing A and B or C is ambiguous. Okay. Writing A and B or C is ambiguous, so one must specify which comes first by writing A and B or C or A and B or C. So in the homework, in the first assignment, where is it? Yeah. So I haven't told you what a truth table is yet, but we will. We're getting to that. Write a complete truth table for the following propositional logic statements. And this one, it compares A and B or C with A and B or C. So doing the conjunction first or doing the disjunction first. And what we'll see is that they're not logically equivalent. They don't always have the same truth value. Sometimes they have the same truth value, but sometimes they don't. So they're not logically equivalent, as we'll find out. So when you're writing things in propositional logic, you have to use these parentheses. Now, in some contexts, so this is a context that is purely propositional logic. In some contexts, conjunction takes precedence over disjunction, but in general context, no. Okay, so you need those parentheses when doing conjunctions and disjunctions. Now, you can write A, as I was saying before, A and B and C. That's fine. That's not ambiguous at all. Or A or B Or C, that's not ambiguous either. But when you're mixing the conjunction and disjunction, you have to specify which comes first. Okay. So now, truth tables. So given a compound propositional logic statement, a truth table, or its truth table, is a table showing the truth value of that statement for each possible truth value combinations of the singular propositions from which it's constructed. Sorry, for the truth value, yeah, combinations of the singular propositions from which it is constructed. So, for example, so let's make a truth table. For A naught and B implies B or A. Actually, I don't need these because of operator precedence. So we'll make a truth table for this. Okay, so I'll remember, because of operator precedence, this statement has parentheses which are unwritten. Well, has parentheses implied. Has the following parentheses implied. Right, A naught and B. It even has one around here, around the knot. A naught and B implies B or A, like that. All right, so but we don't want to write all that. It's way too cluttered. So the less you can write in terms of parentheses, the better. All right, so let's construct this. So we've got two propositions, bare propositions or atomic propositions or propositional variables or whatever you might call them. There's two symbols for the atomic propositions that are used here, A and B. So how many combinations of truth values do we have for A and B, where each one has two? How many combinations are there for A and B?
It's 4.
4. How do you get 4?
2 squared.
2 squared. It's 2 times 2. I know 2 times 2 is equal to 2 plus 2, but in general, it's multiplication. And we'll discuss that in a moment. So A So we have A and B, and the truth value combinations are as follows. So put 2 true, 2 false, and then alternate true, false, and that gives you all 4. So true, 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 false, false, true, false, false. All right, so the first operation or connector that needs to be evaluated is this negation. All right, so A naught. So in the first 2 rows, A is true, so A naught is false. And in the last 2 rows, A is false, so A naught is true. Next, we want to do the conjunction of A naught and B. Or I could do the disjunction of B and A. A naught and B. So I want to do the conjunction. When is the conjunction of A naught and B true? In which row? When is it true?
The third row.
In the third row, because they're both true. Are they both true in any other row? No. So in the rest of the rows, this is false. And then B or A, right? When is B or A false? It's only false when B and A are both false. And in what row does that happen?
4th.
In row 4. In every other row, it's true, because one of A or B or both is true. Okay, and then the last one to be evaluated is the implication. So we have A naught and B implies B or A. This is false when what? The hypothesis is true and the conclusion is false. In what row do we have the hypothesis true? Right here. And in that case, the conclusion is true. So it is never the case that the hypothesis is true and the conclusion is false. So in every case, this is true.
It's a tautology.
It's a tautology, yeah. So propositional logic statements like this one are called tautologies. Okay, they are true for every possible truth value combinations of its propositional variables. So this one is a tautology, and we found that out by making the truth table. Here's another example. And this one won't be a tautology. So let's do the truth table for, so we were talking about this one. A and B implies C if and only if A and B implies C. We were talking about how these were not logically equivalent. So let's actually make the truth table for that and note that it isn't a tautology. Okay, now remember there are implied parentheses here, right? That there are parentheses implied here, here, and here. All right, but we don't want to write all that. It's more cluttered. We want to keep the expression as uncluttered as possible. So we just write this. Okay? All right, so let's make the truth table for that. Now, we have 3 propositional variables inside this statement. So how many rows do you need? How many truth value combinations are there? So we've got 3 propositional variables. Each one has 2 possibilities, true or false. So how many combinations are there altogether? Well, it's multiplied. 2 times 2 times 2. Not 2 plus 2 plus 2. It's 2 times 2 times 2. There's 8 possibilities. All right, so we need a truth table with 8 rows in it. So here's row 1. Well, here's the top for row 1. This one's got to be pretty long. I think I've got one too many. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we go. So there's 8 rows here, and the first 3 columns are going to be the truth values of the propositional variables, A, B, and C. So how do you get all 8 combinations? Well, write down 4 truths, 4 falses for A, first column. Alternate 2 by 2 for the second column, and then alternate 1 by 1 for the third. All right, so if you're familiar with base 2 arithmetic, is anyone familiar with base 2 arithmetic? Representing numbers base 2, or binary arithmetic, I guess?
Yeah.
Yeah. So if you think of f as 0, if you think of f as 0, these are, in reverse order, the numbers from 0 to 7 in binary. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? 0, 1, 2, 3, 4, 5, 6, 7. So if you're familiar with that, if not, we'll actually talk about this later in the course. You already know it. You all know it. You just don't know that you know it, unless you know that you know it. But if you don't know that you know it, you actually know it. And you're wondering how I can say that. It's the same thing. As base 2 is no different really than base 10. The ideas are really exactly the same. The only thing is you only have 2 digits, 0 and 1. But you know, your place value system, the way you add, the way you multiply, all that stuff, it's the same as in base 10. All right, so these are the truth value combinations. So what comes first in this? This one comes last. That's the last connector. All right, that's the last in operator precedence. Which ones come first? You have a few choices actually as to which you can do first. I mean, it's like if you have this 3 times 5 plus 7 times 2. All right, you can do the 7 times 2 first. All right, so this becomes 15 plus 14. All right, so you can do the 14 first or the 15 first, but the addition comes last. Right, so which ones come first? Which one can I do first? Or which one must?
A and B.
A and B, so conjunction A and B. So that's false when both A and B are false, which happens where?
In the 2 last rows.
Yeah, in the 2 last rows, rows 7 and rows 8. So it's false here and here. Oh, I'm sorry. It's true in the first 2 rows. It's true when A and B are both true. I thought I was doing disjunction. When A and B are both true, it's true. Other than that, if one of A or B is false, like in all the other rows, then the conjunction is false. Which one would be next? Which one must be next? There's only one choice. Well, no, actually there's 2 choices, but which one might we do next?
B implies C.
B implies C. That's false when the hypothesis is true and the conclusion is false. When the hypothesis is true and the conclusion is false, which happens here and here. And that's it. So hypothesis true, conclusion false. That only happens in row 2 and row 6. So it's false here. It's false here. It's true everywhere else. In particular, when the hypothesis is false. When the hypothesis is false, the implication is true. So the hypothesis is false in these 2 rows and in these 2 rows, and the implication is true in those 2 rows. Doesn't matter if the conclusion is true or false. The implication is true. All right, next, what might we do? So this one comes last. All right, what might we do next?
We could do A and B implies C.
Sure, A and B implies C. So again, that's false when the hypothesis is true and the conclusion is false. So the hypothesis is true in the first 2 rows, and the conclusion is false in which of those 2 rows?
The second.
The second one only. So that's the only time this is false. It's true everywhere else. So A and B implies C, and then A and B implies C. So that's true when what? When A is true and B implies C is true. When A is true and when B implies C is true. So that's in row 1. A is true and B implies C is true. And not in row 2. A is true. Rows 3 and 4. Right? In row 3, we have A is true and B implies C is true. In row 4, we have A is true and B implies C is true. And then in the last 4 rows, A is false. So whatever B implies C is, doesn't matter. So now the last one is this double implication. So A and B implies C if and only if A and B implies C. So that's true when the truth value of these 2 statements are the same. So it's true here, it's true here, true here, true here, false here, false here, false here, false here. Oh, that's interesting. It's equivalent to A. That can't be right. That can't be right. That it's equivalent to A. Huh. I'll have to think about that. Let me see, make sure we didn't make a mistake. So A and B, true, true. A and B implies C, false.
Isn't
B
okay? Wouldn't A and B imply C? Isn't that row? No, never mind. I'm sorry.
just let's double check here. So B implies C, that's correct. So A and B implies C. True, 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 false. So it's false here. All right. A and B implies C. So true, 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 and false everywhere else. So true, 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 true. Yeah, that's right. Huh. It's logically equivalent to A. Well, that'll be a nice example to do. later. We'll check that later. Anyway, so there's the truth table. So you'll notice that this is not a tautology. Right? Not a tautology doesn't mean always false. It just means not always true. Right? Not always true. So, since I said it, if I was to say to you, not all horses are white, what does that mean? What do I mean? Not all horses are white. Does that mean all horses are not white?
There is a horse that isn't white.
Yeah, there is a horse that some horses aren't white. Right? So if you said all horses are white, that's false. Not because no horses are white, because there is a horse that isn't. Some are brown. Right? Not that there aren't white horses, there certainly are. Right? So a tautology is always true. So not a tautology is not always true. Not always true means sometimes false, not always false. Always false is called a contradiction. So it's the negation of a tautology. All right, so not a tautology. So we see that A and B implies C is not logically equivalent to A and B implies C. So those parentheses that are implied, you have that implied parentheses here, that tell you to do conjunction first and then implication. Here, do the implication first and then the conjunction. They make a difference. Right? They're not the same thing. All right. So now that we've talked about or defined what a tautology is, here are a bunch of tautologies that are commonly used. Well, it's 113 already. Maybe we'll call it a day. Well, I guess we could do one. So these are some named tautologies. So there's a bunch of them. But let's just do a couple in the last minute here. So the implication tautology. So as you might have noticed already, A implies B is logically equivalent to not A or B. Right? If you were to make a truth table to look at this statement, you would see that it is always true. Okay, so remember how I was saying about disjunction, what disjunction means? Disjunction, like if you were to write P or Q, different ways you can write it in English, P or Q. If you don't have P, then you must have Q. If you don't have P, then you must have Q. That means the same thing as P or Q. Right? It means the same thing, but it's a way of changing implication into a disjunction, and that's called the implication tautology. And that's an important one. So here I have the negation here rather than here, but that doesn't matter. So that's the implication tautology, and then there's some other ones that go along with implication. A implies B is logically equivalent to B naught implies A naught. So A implies B, like I was saying, it's this containment relation. A is contained within B. Well, if A is contained within B, certainly it's not the case that B is contained in A, right? If you're a student in my class, then you are a student at Wright State. That's true, right? You guys that are with me today, you are students at Wright State. But it's not true the other way around. If you're a student at Wright State, then you're a student in my class. That's not true at all, right? But if you do want to flip it around, you can. You just have to negate. If you're not a student at Wright State, then you're not a student in my class. It means the same thing. Right? If you have an apple, then you got it from a tree, somehow, ultimately. If you have an apple, then it ultimately came from a tree. Right? If ultimately it didn't come from a tree, then you don't have an apple. Okay, so that's the contrapositive tautology. There's a bunch more we'll go over next time. Okay, so we're going a little slower than I thought we would. Probably I'm going to change the due date for the first assignment, maybe push it to Friday. But I'll let you know. But please get started on it. You know, the first problem is about truth tables, so you can at least do that one. All right. Okay. So we'll see you next time. Any problems or concerns, just email. Questions or concerns, just email me. Okay. All right. Have a good afternoon, everybody.